Hello there, and welcome to the Sleepy Space Channel. Europa is the moon we name whenever anyone asks where life might be waiting, and its surface is the most lethal ground in the solar system. A person standing on that ice in an ordinary suit would take a fatal dose of radiation in slightly under a day, and would feel nothing at all while it happened. The same is true, differently, of every world Jupiter holds. Io repaving itself in molten sulfur, Ganymede shielded by a magnetic field of its own, Callisto old and dark and quietly the only ground a person could stand on. Tonight we visit all four and ask what would really happen to anyone who tried to stay. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away behind you. Let's begin. Part 1. The planet that owns them all. Jupiter has more than 90 moons, and 4 of them are worlds in every sense that matters. They have oceans and volcanoes and magnetic fields and skies. 2 of them are larger than the planet Mercury. One of them holds more liquid water than every ocean, sea, lake and river on Earth combined, and holds it in the dark, under a shell of ice, at a distance from the sun where liquid water has no business existing at all. For most of the last century, these 4 moons have sat near the top of every list of places we might one day go. There is a sobering thing about that list, and it is worth stating plainly before we go any further. The moon that appears at the very top of it, the one that gets named more often than any other, the one that carries the word ocean in front of it every time it is mentioned, has the most lethal solid surface anywhere in the solar system that a person could physically stand on. Not the hottest, not the most crushing. The most lethal, in the specific sense that a human being standing on it in an ordinary pressure suit would receive a fatal dose of radiation in slightly under a day, and would feel nothing at all while it happened. That moon is Europa. We will spend a long time there tonight, because it deserves it, and because almost everything people believe about it is arranged in the wrong order. But before we go to any of these moons, we have to understand the thing that all 4 of them orbit, because the single most important environmental fact about every world in this system is not the ground beneath it. It is the planet above it. Jupiter is not simply a large planet with satellites. Jupiter is a magnetic environment, and the moons live inside it. Deep within the planet, far below the banded cloud tops, hydrogen is compressed until it stops behaving like a gas and starts behaving like a metal. Its electrons come loose and move freely, and an enormous shell of that liquid metallic hydrogen churns and circulates in the planet's interior. Jupiter turns on its axis once every 10 hours, faster than any other planet, and that combination, an ocean of electrically conducting fluid, spun very quickly, generates a magnetic field of a strength that has no rival anywhere in the solar system except the Sun itself. At its source, that field is roughly 20,000 times stronger than Earth's. It extends millions of kilometers out toward the Sun before the solar wind is finally able to push back against it, and it streams away in the other direction in a long tail that reaches past the orbit of Saturn. If that structure glowed at wavelengths our eyes could see, it would appear in our night sky several times wider than the full moon, despite lying more than 4 times farther away from us than the Sun. The field itself is invisible and harmless. What the field does is not. A magnetic field of that strength captures charged particles. Electrons and ions that would otherwise sail past the planet and continue on their way instead become trapped on the field lines, bouncing back and forth between the magnetic poles, gaining energy with each pass, until some of them are moving at a substantial fraction of the speed of light. Earth has the same phenomenon. We call them the Van Allen belts, and they are the reason crewed spacecraft in low orbit stay beneath them, and why the few missions that crossed them did so quickly. Jupiter's version of the same structure is more intense by something close to a factor of 10,000. The scale of it was apparent long before anything of ours went there. Jupiter is one of the brightest radio sources in our entire sky, and radio astronomers detected the emission from those belts decades before any spacecraft left Earth, without at first understanding what they were listening to. There is also a boundary far out in front of the planet, a standing shock front where the oncoming solar wind is abruptly slowed, and a spacecraft crosses that front hours or even days before it reaches Jupiter itself. By the time a probe sees the planet as a disk, it has already been inside Jupiter's influence for a very long while. And the four great moons do not orbit near those belts. They orbit inside them. Only the outermost of the four sits far enough from the planet to escape the worst of it, and that single fact will turn out to reorder everything we think we know about where a person could actually live in this system. There is a further detail that makes the situation worse, and it is a matter of timing rather than strength. Jupiter rotates once in about 10 hours, and the magnetic field, anchored in the planet's interior, rotates with it. The innermost of the four large moons takes about 42 hours to complete an orbit. The second takes about 85 hours. The third takes around 172, and the fourth roughly 400. Every one of them is being continuously overtaken by the field and by everything trapped in it. The consequence is that the moons are not merely sitting in a hazardous region. They are being swept. The trapped plasma rushes past them at tens of kilometers per second, striking one hemisphere of each moon far harder than the other, driving chemistry down into the surface, knocking atoms off it and into space, and continuously replenishing itself from behind. A moon in this system is not protected by being made of solid material. It is sandblasted, permanently, on a schedule set by the rotation of a planet a long way overhead. The field is also not tidally aligned. Its axis is tilted about 10 degrees from the axis Jupiter spins on, and it is offset from the planet's center besides, so the whole structure wobbles as the planet turns. For any fixed point on the surface of any of these moons, that means the dose is not steady. It rises and falls through every 10-hour cycle as the tilted belts sweep up and then down past the moon's position, and a settlement would have hours in which stepping outside was merely very bad, and hours in which it was considerably worse. There is one more piece of the machinery to set in place, and it is the piece that gives this system its oceans. The three inner large moons are locked into a precise gravitational relationship with one another. For every 4 orbits the innermost one completes, the second completes exactly 2, and the third exactly 1. That arrangement is not a coincidence of this particular era. It is a stable configuration that the moons settled into very early and have held ever since, and it quietly governs almost everything that happens to them. A moon traveling on a perfectly circular path around a planet feels a steady, unchanging pull and does not deform. A moon traveling on an elliptical path is squeezed harder when it swings close and relaxes when it drifts far, and that endless cycle of deformation generates heat inside it, through friction, in the same way a paperclip grows warm when it is bent back and forth. Left to itself, that process would use up the eccentricity of the orbit and round it out, and the flexing would gradually stop. In this system it never stops, because the 3 moons tug on one another at the same point in every cycle, and keep each other's orbits stretched. The result is a heat engine that has been running for billions of years and has nothing left to run out of. It is the reason the innermost of these moons is the most volcanically violent object we know of. It is the reason the second one has a liquid ocean beneath its ice, at a place 5 times farther from the sun than we are. And it is the reason the outermost of the 4, which sits alone outside that relationship, is cold and quiet and geologically dead. Everything else follows from those two facts: the field and the resonance. One of them makes this system dangerous. The other one makes it interesting. And as we go from moon to moon tonight, it will become clear that they are not two separate stories at all, but the same story told from two directions. There is one last number to carry with us, and it is a gentle one. Jupiter orbits at about 5 times our own distance from the Sun, which means the sunlight arriving there is roughly 1/27th of what falls on Earth, a little under 4%. Noon on any of these moons is about as bright as a heavily overcast afternoon at home, and the Sun has no disk to speak of. It is simply the brightest star in a very dark sky. Everything that happens out here happens in that dimness, and nothing that lives there, if anything does, has ever seen the Sun at all. Part 2. Europa, and the ground you would be standing on. Europa is the smallest of Jupiter's 4 great moons, and it is a little smaller than our own, about 3,100 kilometers across, against the Moon's 3,470. It orbits at roughly 670,000 kilometers from Jupiter and completes a circuit in 3.5 days. Like all 4 of the large moons, it is tidally locked, which means one hemisphere faces the planet permanently and the other faces permanently away. Its surface gravity is about 1/7 of Earth's, which is slightly weaker even than the Moon's. A person of 70 kilograms would register a little over 9 kilograms on a scale there. A dropped tool would take about 1.5 seconds to fall the height of a table. And the surface it would fall onto is water ice, the smoothest solid surface of any large body in the solar system. That word smooth deserves unpacking, because it is not a poetic description. There are no mountains on Europa in any sense we would recognize. The greatest vertical relief anywhere on the Moon amounts to a few hundred meters, which on a body of that size is roughly equivalent to the imperfections on a billiard ball. Seen from orbit, Europa reads as a pale, cracked eggshell, bright, almost featureless in relief, and covered in a network of dark lines that look drawn on rather than carved in. The reason it is so smooth is the reason everything else about Europa is interesting. The surface is new. Crater counting is the standard way of dating a surface anywhere in the solar system. The logic is simple. The longer a piece of ground sits exposed, the more impacts it accumulates, so the crater density tells you roughly how long it has been there. Apply that method to Europa, and the answer comes back somewhere between 40 and 90 million years. Essentially, none of the ground you would be standing on existed when the last of the dinosaurs did. There are perhaps 24 craters larger than a few kilometers across on the entire Moon. On the outermost of Jupiter's great moons, which we will reach later tonight, the situation is exactly reversed. There are so many craters that new impacts can only erase old ones, and the surface has run out of room. Europa's surface is being erased and rewritten continuously by something arriving from below. Look closer, and the drawn-on lines resolve into the Moon's dominant feature. They are called lineae, and they are cracks. Some of them run for more than 1,000 kilometers. Some are 20 kilometers or more across. They appear reddish-brown against the white ice, and they cross and overlie one another in a tangle that records episode after episode of fracturing, each generation cutting across the one before it. They form because the ice shell is being flexed and it breaks. Material from beneath, briny water, or warmer ice, or some slush between the two, rises into the opening and freezes there. Many lineae have a characteristic double structure, 2 parallel ridges with a shallow valley running between them, which is what you get when a crack opens and closes repeatedly and pushes material up along both margins each time. Some of them are stranger than that. A number of the cracks are cycloidal. They curve in a chain of arcs, one scallop joined to the next, like the pattern a child might draw along the edge of a page. That shape is a fingerprint. A crack, propagates in the direction the stress field pushes it, and if that stress field is slowly rotating while the crack travels, the crack curves. The stress field on Europa rotates because the Moon flexes on a 3.5-day cycle as it goes around Jupiter. Those arcs are among the strongest visual evidence anywhere on the Moon that its shell is not rigidly attached to whatever lies beneath it, that it is, in some sense, floating. In other places, the surface abandons order altogether. These regions are called chaos terrain, and they are exactly what the name suggests. The ice has broken into blocks tens of kilometers across, which have visibly rotated, tilted, and drifted away from one another before setting again in new positions. Some of those blocks are recognizably fragments of older lineae, now shifted and turned so that the lines no longer meet across the gap between them. You can read the displacement directly, the way you can read the movement of ice flows in a photograph of a frozen sea in spring. There is no way to produce that appearance in a shell that is solid all the way down. Something beneath had to be mobile enough to let pieces of ice the size of small countries move around and then freeze into place again. Chaos terrain covers a substantial fraction of the Moon, and it is the visual argument for what lies underneath. There are gentler features too, easy to miss among the fractures. Scattered across the Moon are lenticulae, small dome-shaped rises, a few kilometers across, where the surface has been pushed upward from below without ever breaking open. They appear to be places where a pocket of warmer, more buoyant ice has risen slowly through the shell and lifted the ceiling above it, the way a body of salt rises through rock on Earth over geological time. The domes are low and rounded, and in an image they read almost as blisters. They are the quietest evidence Europa offers that its shell is alive. The craters, too, tell a story simply by being the wrong shape. Impact craters on Europa are unusually shallow for their diameter, flatter than the same-sized crater would be on a rocky body, and flatter than they would be in ice that continued solid all the way down. That flattening is what you expect when something strikes a layer that is not thick, and when the material beneath that layer can rise back up afterwards. And the ice itself is exceptionally bright. Europa reflects roughly 2/3 of the light that falls on it, one of the highest values of any large body we know, which is part of the reason its surface stays as cold as it does. It keeps almost nothing. Then there is the cold, and the cold changes the character of the ground entirely. Surface temperatures on Europa run from about 110 Kelvin at the equator down to around 50 Kelvin near the poles, roughly -160 and -220 degrees Celsius. Water ice at those temperatures is not the substance we know from a freezer. It is not soft, it does not become slippery underfoot, and it does not carve easily. Its compressive strength approaches that of granite. It fractures in a brittle way, rather than yielding, and it will blunt equipment designed for ice and behave like rock instead. For anyone trying to build there, this is not a detail. Drilling into European surface ice is a rock mining problem. Anchoring anything into it is a rock anchoring problem. And all of it has to be done with machinery that stays warm enough to keep working while standing on a surface that will pull heat out of it continuously and give nothing back. Above that ground there is an atmosphere, technically, and it is close enough to nothing that the word is almost misleading. Surface pressure on Europa is on the order of 1/10 of a micropascal. That is roughly 100 trillionth of the pressure at sea level on Earth, and it is a better vacuum than most laboratories on Earth are able to produce deliberately. What is there is molecular oxygen, and it is worth being clear that this is not a hopeful sign. It did not come from anything living. Radiation striking the ice breaks water molecules apart, the light hydrogen escapes to space almost immediately, and the heavier oxygen lingers a little longer before it too is lost. Europa's atmosphere is a continuously regenerated byproduct of its own surface being destroyed. It is oxygen, and it is entirely useless. There is not enough of it there to be anything at all. And there is one more possibility about the ground, unconfirmed but taken seriously, which is worth sitting with for a moment. Under the right conditions, sunlight, sublimating an icy surface unevenly, can carve it into penitentes, forests of upward-pointing blades, formed as some patches vaporize faster than others. On Earth, they appear in high, dry mountain snowfields and reach a meter or two. Modeling of Europa's particular combination of temperature, vacuum, and low-angle light suggests that if they form there, they could be far larger. Possibly 15 meters tall. Possibly spaced a few meters apart. Possibly covering enormous stretches of the equatorial belt. Nobody has ever landed on Europa, so nobody knows. But it is a curious thing to hold in mind that large regions of the most talked-about destination in the outer solar system may be covered in fields of hardened ice spikes taller than a house, standing in permanent dimness, in a place where the first thing to touch them will be something we scent. Part 3. The figure that decides everything. Everything we have described so far, the ice, the cracks, the chaos, the cold, is the part of Europa that a photograph can show. What follows is the part that no photograph shows, and it governs the Moon completely. The surface of Europa receives an ionizing radiation dose of roughly 5.5 sieverts per day. That number needs a scale beside it to mean anything, so here is one. A whole-body dose of 1 sievert delivered at once produces acute radiation sickness. A dose of 5 sieverts is around the level at which roughly half of untreated adults die within a month. 8 to 10 sieverts is fatal essentially without exception, regardless of what medicine is brought to bear. Standing on the surface of Europa in an ordinary pressure suit, a person accumulates the half-lethal dose in about a day, and an unambiguously fatal one in under 2. The point at which the first symptoms appear, nausea, weakness, damage to the bone marrow that will not be apparent for hours, arrives in well under a single hour, and nothing about it is perceptible. There is no heat, no glow, no sound, no smell, no sensation of any kind. The particles pass through the suit, through the skin, through the cells, breaking molecular bonds as they go, and the body has no receptor for any of it. A person could stand on Europa's ice under a hanging planet, in complete comfort, taking readings, planting instruments, and be receiving a dose rate that would empty a nuclear facility on Earth within seconds of the alarm sounding. The suit would report it. The body would not. The dose comes almost entirely from high-energy electrons trapped in Jupiter's belts, and Europa orbits deep inside them. These electrons arrive with energies in the tens of millions of electron volts, which is high enough to pass straight through several millimeters of aluminium. There is a further problem, and it is the sort of detail that catches engineers out. Thin shielding can make things worse. When a very fast electron is stopped abruptly in a dense material, it gives up its energy as penetrating X-rays, a process with the German name Bremsstrahlung, breaking radiation. Put a thin sheet of lead between a person and Europa's electron flux, and you have converted one fast particle into a shower of X-rays that the lead is too thin to absorb. This is why shielding designs for the Jovian system favor light materials, water, polyethylene, ice, over the heavy metals that intuition suggests. What you want is a great deal of something light, not a little of something dense. It is worth placing Europa's figure next to the numbers we use at home, because the gap is not the kind that intuition handles well. A person living at sea level on Earth receives a few thousandths of a sievert in a year from natural background, cosmic rays, radon, the potassium in their own body. Career limits for people who work with radiation professionally and for astronauts are set well below a single sievert accumulated over an entire working life. Europa's surface delivers that entire career allowance in a few hours. The intensity of the environment there exceeds the intensity inside Earth's own radiation belts by something close to 4 orders of magnitude. Machines fare no better, only more slowly and more predictably. Radiation damage in electronics is cumulative and largely irreversible. Each passing particle displaces a little charge in the insulating layers of a transistor, and over time, those small displacements shift the voltage at which the transistor switches, until circuits that were designed with margin no longer have any. There is no repair mechanism and no recovery period. A spacecraft in the Jovian system is not wearing out mechanically. It is being slowly rewritten at the level of its own logic. The dose is not perfectly uniform across the Moon, though the variation is a matter of degree rather than of kind. The trailing hemisphere, the side that faces into the sweeping plasma flow, the side being run into rather than run away from, takes a substantially heavier dose than the leading hemisphere. High latitudes fare better than the equatorial band. Those differences are large enough to matter a great deal for planning a landing, and not nearly large enough to make anywhere on Europa safe. The best place on Europa is still catastrophically worse than the worst place on Mars. But the radiation does not merely pass through Europa's surface and leave it as it was. It rewrites it. When energetic particles strike water ice, they break the molecules apart, and the fragments recombine into compounds that were not there before. The process is called radiolysis, and on Europa, it has been running without interruption for as long as the surface has existed. The products are molecular oxygen, hydrogen peroxide, and a range of other oxidizing compounds. Europa's ice carries hydrogen peroxide at concentrations far above anything that could survive on a quieter world, because on a quieter world there would be nothing continuously making it. Then there is the sulfur, and the sulfur comes from a neighbor. The innermost of Jupiter's great moons is venting roughly a ton of material into the system every second, and a great deal of that material is sulfur compounds. Once it escapes, it is ionized, picked up by the magnetic field, and carried around the planet. Some of it is driven directly into Europa's trailing hemisphere. Combined with the radiolysis already underway, the result is sulfuric acid in hydrated form, and it makes up a meaningful fraction of everything on that side of the Moon that is not water ice. So here is the honest description of the ground on the most celebrated destination in the outer solar system. It is bleached, hardened water ice at 110 Kelvin, laced with peroxide and hydrated sulfuric acid, bombarded continuously by particles moving at a fraction of the speed of light and slowly eroding into space. That last part is literal. Alongside the chemistry, the bombardment physically knocks atoms and molecules loose from the surface, a process called sputtering, and Europa loses something on the order of tens of kilograms of material per second this way. The Moon travels inside a faint donut of its own escaped gas, following it around Jupiter, a thin torus of Europa, strung out along Europa's orbit. For anything we would bring there, the combination is unlike any environment we have ever engineered for. Hard vacuum, deep cold, penetrating radiation, and an oxidizing acidic dust, all at once, all continuously. Seals, polymer components, optical coatings, wiring insulation, fabrics, every one of those has a failure mode under each of those 4 conditions separately, and we have no test chamber on Earth that reproduces all 4 together. Anything sent to Europa's surface is being tested for the first time by the surface itself. The contamination is visible too, if you know to look for it. The leading and trailing hemispheres of Europa differ noticeably in color and in composition, and the boundary between them is not a geological one, it is a directional one, drawn by which way the Moon happens to be facing as it travels. One side is whiter and cleaner. The other is stained. Nothing on the Moon put that line there. The line was painted on from outside by the planet over millions of years. And there is a turn in all of this that will matter later, so it is worth planting now. The same radiolysis that makes the surface uninhabitable is manufacturing oxidants, peroxide, molecular oxygen, reactive compounds, and depositing them in the topmost layer of the ice. If any of that material is carried downward, through the cracks or by the slow overturn of the shell, it arrives in the ocean below as chemical energy. On Earth, life runs on the meeting of something oxidizing with something reducing. The bombardment that would kill anyone standing on Europa may be the very thing that supplies the ocean beneath them with something to live on. You can see the shape of that constraint in how the missions are actually built. The most capable spacecraft ever sent to study Europa does not orbit Europa at all. It orbits Jupiter instead, on a long looping path that carries it far out of the worst of the belts, and it makes repeated brief flybys of the Moon, dozens of them, each lasting hours. Its electronics live inside a thick-walled metal vault. The reason for the whole arrangement is arithmetic. A spacecraft placed in a permanent orbit around Europa would be destroyed by accumulated dose in a matter of weeks to months. The mission is designed around a radiation budget the way an aircraft is designed around a fuel budget, and every pass spends a measured portion of the vehicle's remaining life. That arithmetic is why the dose figure decides everything about human presence too, and why it decides it so quickly. Shielding scales with mass. Mass must either be carried 5 astronomical units from Earth or found on site. And the one abundant shielding material on Europa is the ice itself. Which means that the answer to the radiation problem on Europa is not a better suit, or a thicker wall, or a hardened vehicle. The answer is depth. A meter of ice cuts the dose substantially. 10 meters brings it down to something a body could tolerate indefinitely. 100 meters makes it a non-issue entirely. The place to live on Europa is not on Europa. It is inside it. And as we are about to see, that solution has a set of difficulties all its own. Part 4. The ocean and the problem of going down. The ocean under Europa's ice is not a hopeful guess. It is a measurement, and the measurement is a magnetic one. Jupiter's magnetic field is tilted with respect to its rotation axis, which means that as the planet turns, the field at Europa's position swings back and forth in direction. Any electrically conducting material inside the Moon responds to that changing field by generating a field of its own, opposing the change, the same effect that appears in a coil of wire moved near a magnet. That induced signature has been detected at Europa, and it is strong, and it requires a globally connected layer of conducting fluid lying within roughly 100 kilometers of the surface. Pure water ice does not conduct electricity. Salty liquid water does. The magnetic reading effectively rules out the alternatives, and everything the surface has been telling us, the cycloidal cracks, the drifting chaos blocks, the shallow craters, the near-total absence of an impact record, points the same way. There is water down there, and it is connected all the way around. The scale of it is the part that resists being held in the mind properly. The ice shell is thought to be somewhere between 15 and 25 kilometers thick. Beneath it, the liquid layer runs 60 to 150 kilometers deep. Earth's oceans average about 4 kilometers. Europa's ocean is somewhere between 15 and 40 times deeper than ours, wrapped around a body a quarter of Earth's diameter, with no continents interrupting it anywhere. Add up the volume and it comes to roughly twice all the liquid water on Earth. Every ocean, every sea, every lake and river, every drop of groundwater in every aquifer, doubled, and held on a moon smaller than our own. It is very probably the largest single body of liquid water anywhere in the solar system. And it is dark. Not dim, not shadowed, absolutely dark, in a way that no place on Earth's surface has ever been. 15 to 25 kilometers of ice transmits no light at all. Whatever occurs in that water occurs without a single photon of sunlight ever having reached it, and has done for as long as the ocean has existed. It is salty, though exactly how is still being worked out. The candidates have been magnesium sulfate salts on the one hand and sodium chloride on the other, and spectra of places where ocean material seems to have reached the surface have leaned lately towards sodium chloride, ordinary table salt. If that reading holds, Europa's ocean is chemically rather less alien than anyone expected. It is seawater. It is cold, and it is under a great deal of pressure, and it has never been seen, but it is seawater. The pressure is considerable. At the base of a water column, 100 kilometers deep, even in 1/7 of Earth's gravity, and with the weight of 20 kilometers of ice pressing down from above, the figure comes out at something like 130 to 160 megapascals. That is well over 1,000 times the atmospheric pressure at Earth's sea level, and appreciably greater than the pressure at the deepest point in the Pacific, where the water column is only 11 kilometers tall but sits in a much stronger gravitational field. And beneath all of it, most likely, is rock. A silicate mantle, and beneath that, an iron core. That single structural detail is the most important thing about Europa, and it is why this moon, and not another, is the one everybody names. Water in contact with rock does chemistry. Minerals dissolve. Hot rock and cold water react in ways that release hydrogen. Where heat escapes from a planetary interior into an ocean, hydrothermal systems form, chimneys, vents, plumes of chemically loaded water rising into cold, dark surroundings. On Earth, those places support entire communities of organisms that have no need of sunlight at all and never encounter it. If Europa's ocean touches its rock, and the tidal heating that keeps that ocean liquid also keeps the seafloor warm, then the same arrangement may exist there. Larger, older, undisturbed for billions of years. There are qualifications worth keeping. The ocean may be stratified, with dense brine settling at the bottom and fresher water above it, and if the layers do not mix readily, then whatever chemistry happens at the seafloor may never reach the underside of the ice, and whatever oxidants arrive from above may never reach the rock. An ocean can be enormous and still be divided. There is also the question of how much energy is actually available. Sunlight delivers a colossal amount of power to Earth's surface every second, and the entire chemical budget of Europa's ocean is a small fraction of that. Any biosphere there would be sparse and slow rather than crowded, thin communities clustered at the places where the chemistry is strongest, with a great deal of empty water in between. And the shell may not be uniformly thick. Some models allow for regions where the ice thins to a few kilometers rather than 20, and some of the chaos regions may mark exactly those places, spots where warm water has come close enough to the surface to break it up from below. If such thin patches exist, they are where anything we send will go. There have also been indications, more than once, of water vapor rising above Europa in plumes, which would be an extraordinary convenience if confirmed, a way to sample the contents of that ocean by flying through what it has already thrown into space, without ever having to land at all. That is the case for Europa, and it is a good one. Now here is what it would actually take to be there. The obvious answer to the radiation problem, as we have seen, is to go down. 10 meters of ice, and the dose becomes something a body could live with. 100 meters, and it stops being a consideration at all. Below that depth, Europa is, in radiological terms, one of the safest places in the solar system, quieter than the surface of Earth, because there is no radon and no cosmic ray flux reaching that far in. The difficulties start immediately afterwards, and they do not stop. Ice at 110 Kelvin is as strong as granite, so the shaft has to be cut through rock-equivalent material with equipment operating in vacuum at cryogenic temperature. Worse, the shaft does not stay open. Ice under pressure at depth deforms plastically. It flows very slowly under its own weight, and it closes any opening left in it. Every permanent route down would have to be actively maintained or permanently lined, and the lining would have to tolerate that same slow squeeze indefinitely. Then there is the fact that the shell itself is not a foundation. Chaos terrain is direct evidence that large sections of Europa's ice have broken apart and rearranged themselves, repeatedly, within the last few tens of millions of years. The time scale is long by the standards of a human life and short by the standards of a world. What it means practically is that there is no bedrock on Europa. There is nothing to build on that will still be in the same place or the same orientation in geological time. Anything built into the shell is built into a raft, and the raft flexes. Europa's solid surface rises and falls by up to about 30 meters over each 3.5-day orbit, as Jupiter's pull strengthens and eases. That is a tidal range comparable to the very largest on Earth, except that here it is happening in solid ice rather than in water, and it is happening to whatever has been anchored into it. The flexing cracks the shell, and the cracking produces icequakes. A shelter buried in Europa's ice would experience a full mechanical loading cycle every 85 hours, for as long as it stood, with nothing anyone could do to reduce the amplitude. Reaching the ocean itself is a further problem again, and a genuinely unsolved one. The deepest hole ever drilled on Earth reached about 12 kilometers, took roughly 2 decades, and was made at a site with full industrial support, breathable air, and gravity helping to lower the drill string. Europa's shell may be twice that thick, at cryogenic temperature, beneath a lethal sky, 5 years from resupply. The leading concepts are thermal rather than mechanical. A probe carrying a radioisotope heat source that simply melts its way downward, letting the water refreeze above it as it goes. Such a machine descends slowly, over months or years. It cannot be recovered. It severs its own physical path back to the surface behind it. It communicates through a trailing tether or through sound conducted up the ice, and whatever it finds down there, it stays. There is something quietly fitting in that. The first thing of ours to reach that ocean will almost certainly be a machine that was never designed to come back, and it will spend the rest of its existence in the dark water, in the largest sea in the solar system, having sealed the door behind it on the way in. Part 5. The body, the sky, and the day that is not one. Suppose all of it were solved. Suppose the shaft were cut and lined and maintained, the shelter buried deep enough that the dose no longer registered, the power supplied, and the water melted and the air made. There would still be the question of what it does to a person to be there, and that question divides neatly into 3 parts: what the gravity does, what the vacuum does, and what the sky does. Europa's surface gravity is about 1.3 meters per second squared, a little over 1/7 of Earth's, and slightly less than the Moon's. A person could jump about 7 times as high as at home, and would hang in the air for around 2.5 seconds coming back down from a modest hop. Walking, in the ordinary sense, would not work. The foot leaves the ground too readily, and the body has too little weight pressing down to generate any useful friction, so the gait that develops is a low, bounding lope, pushing off with both feet, which is what happened on the Moon within minutes of anyone trying. It looks effortless, and it is, in one specific respect only. A person on Europa would weigh less than a large dog does on Earth, but they would still have all of their mass. The inertia is unchanged. Starting is easy, and stopping is exactly as hard as it has ever been, and the mismatch between those 2 things is the thing that catches people out. The medical question is not about novelty. It is about duration, and about a gap in what we know that is larger than most people realize. In weightlessness, the human body responds by discarding what it is no longer being asked to maintain. Bone mineral density falls by roughly 1 to 2% per month, concentrated in the load-bearing skeleton, hips, spine, legs. Muscle mass declines. Fluid shifts toward the head and changes the shape of the back of the eyeball, altering vision in a substantial fraction of long-duration crew members, sometimes permanently. The cardiovascular system deconditions because it is no longer pumping against a column of blood. We have decades of careful data on all of that at 0 gravity, and we have all of human history at 1 gravity, and we have almost nothing at all in between. Nobody has ever lived for an extended period at any intermediate value. It is possible that some modest fraction of Earth's gravity is enough to switch the maintenance systems back on, and that 1/7 would be sufficient. It is equally possible that the body's response is closer to a threshold than a slope, and that 1/7 of a gravity is, physiologically, indistinguishable from none at all. Nobody knows, and the only way to find out is to go and find out. The vacuum question is simpler and less forgiving. At 1/10 of a micropascal, there is no meaningful distinction between the outside of Europa and open space. A suit breach is not a situation to be managed, but an event to be survived in seconds. The water in soft tissue begins to vaporize almost immediately, swelling the body, a process called ebulism, and the air in the lungs must be released at once, because holding it would tear them as it expands. Consciousness goes in roughly 10 to 15 seconds as the last oxygenated blood leaves the brain. The cold, counterintuitively, is the least of it. Vacuum is an excellent insulator, and a body in it loses heat only by radiation and by evaporation from exposed moisture, which is slow. A person exposed on Europa's surface would be gone long before freezing became relevant to the outcome. There is also the matter of what falls out of the sky. Earth's atmosphere destroys almost every small particle that arrives. Europa has no such filter, so grains of dust strike the surface at tens of kilometers per second with the energy of a bullet. The flux is low enough that the chance of any particular person being struck in any particular hour is very small. It is high enough that over the operating life of a large habitat, it becomes a structural requirement rather than a hypothetical. There is one genuinely favorable engineering fact in all of this, and it is worth naming because there are so few. Europa's escape velocity is about 2 kilometers per second. Earth's is a little over 11. Leaving Europa is cheap. A small vehicle with a modest tank could lift off that surface and reach orbit around Jupiter, which is a very different situation from standing at the bottom of a planetary gravity well and needing an entire launch industry to get out of it. Whatever else is difficult about being on Europa, departing is not. And outside the habitat there would be no sound at all. Not quiet, none. There is no medium to carry it. A rock fall 100 meters away would be entirely silent. A plume of vented gas would be silent. Machinery working nearby would be silent. The only things audible would be those transmitted mechanically through the structure itself, the hum of whatever is running, footsteps along a floor, and the ice, occasionally, settling and cracking somewhere in the shell around you and arriving through the walls as a low sound with no direction to it. And then there is the sky, which is the one part of all this that is simply beautiful. Jupiter, from the hemisphere of Europa that faces it, spans roughly 12 degrees. That is about 24 times the apparent width of the full moon from Earth, and something like 500 times its apparent area. Held at arm's length, an outstretched hand would cover perhaps 2/3 of it. It is not a light in the sky. It is a wall, banded in cream and ochre and rust, with storms visible on it as distinct features, and cloud belts sliding steadily across its face as the planet turns beneath them every 10 hours. And it does not move. Europa is tidally locked, so Jupiter hangs at a fixed point overhead, permanently, and has done since the moon settled into that lock billions of years ago. It does not rise. it does not set. It does not drift with the season, because there is effectively no season. Europa's axis is very nearly upright. From the far hemisphere, Jupiter is never visible at all. Someone living there would have no direct evidence of the planet's existence from the ground, only a sky full of stars and a very small, bright sun. And along the line between the two hemispheres, Jupiter sits permanently on the horizon, half above it and half below, in the same position forever. It has phases, cycling through them every 3.5 days as Europa travels around. And once each orbit, Europa passes into Jupiter's shadow. The eclipse lasts a little under 3 hours. The Sun goes behind a dark disk 12 degrees wide, and around the edge of that disk appears a thin, brilliant ring where sunlight is refracted through Jupiter's upper atmosphere, a circle of red-orange light, drawn from every sunrise and sunset happening simultaneously around the whole limb of the planet. Then the Sun comes back. Every 85 hours, without fail, for as long as the Moon has been there. The lighting on the two hemispheres is not the same either, and the difference is Jupiter's doing. The planet is enormous and reasonably bright, and it reflects a real quantity of sunlight down onto the hemisphere facing it. Night on the sub-Jovian side of Europa is never fully dark. There is always that great pale face overhead throwing down a soft colored light, considerably brighter than a full moon at home. Night on the far side is genuinely dark, lit only by stars and by a sun that has set. Two hemispheres of the same small moon, one of them permanently under a lamp and the other permanently without one, and no one ever crossing between them without noticing. As for the sun itself, it delivers about 1/27th of the light it gives Earth, which sounds dire and is less so than it sounds. Sunlight at Europa is still roughly 1,000 times brighter than a full moon on a clear night at home. Daylight there is dim, not dark. A person could read outdoors. It would simply feel, permanently, like the light half an hour before a storm. There is a further glow, fainter and stranger. Where Jupiter's plasma strikes Europa's tenuous atmosphere, aurorae form, and the ice itself has been observed to glow faintly on the night side, lit not by any external source, but by the bombardment landing on it. The surface shines because it is being struck. What Europa does not have is a day. There is no 24-hour cycle, no seasonal cycle worth the name, and no natural rhythm anywhere near the length of a human one. What is on offer is a 3.5-day orbit, an eclipse within it, and the 10-hour turning of an enormous face that never changes position. A human settlement there would have to manufacture its own day out of artificial light, on a schedule invented rather than inherited, and maintain that invention indefinitely, because the moment it lapsed, there would be nothing outside to correct it against. Part 6. Io, the neighbor that fails in a different direction. Inward from Europa, closer to Jupiter than any other large moon, lies Io. It orbits at about 420,000 kilometers from the planet and goes round in a little under 42 hours. It is slightly larger than our own moon, and it is the densest moon known anywhere, rock and metal almost entirely, with essentially no water in it at all. That last point deserves a moment, because it inverts the expectation. Io sits 5 times farther from the Sun than Earth does, in a region where water ice is the most common solid material available, surrounded by neighbors that are largely made of it, and it is the driest place in the outer solar system. Whatever water Io began with was driven off long ago by the same process that dominates it now. Io is the most volcanically active object in the solar system, and the margin is not close. More than 400 separate volcanic centers have been identified on a body the size of our moon, and the total heat flowing out of its interior amounts to something on the order of 100 trillion watts. The engine is the resonance. Io's orbit is held permanently elliptical by its gravitational conversation with Europa and Ganymede, and Jupiter's pull on it varies enormously across that ellipse. The solid body of Io is deformed by as much as 100 meters over each 42-hour cycle, an entire rocky world being kneaded like dough twice a day without pause. The friction from that deformation is where the heat comes from, and the supply does not run down, because the resonance keeps handing back the eccentricity that tides would otherwise remove. Beneath the crust, there is very probably a global layer of partially molten rock, a magma ocean, inferred from the way Io responds magnetically to Jupiter's changing field. It is the same induction technique that revealed water beneath Europa, applied to a body where what it found was not water at all. The consequences at the surface are difficult to overstate without reaching for words this channel does not use, so we will use numbers instead. Io resurfaces itself at an average rate of roughly a centimetre per year across the whole moon. That is enough to bury anything placed on the ground within a human lifetime, and it is why Io has almost no impact craters. It is not protected from impacts. It simply paves over them faster than they can accumulate, which is the exact opposite of the situation on the outermost of these moons, and, in its way, an even more thorough kind of erasure. Its plumes rise to heights of hundreds of kilometers. The largest reach something like 500 kilometers above the surface, which is roughly the altitude at which spacecraft orbit the Earth. With no thick atmosphere to slow them, the ejected material follows clean ballistic arcs and comes back down in near-perfect circles, which is why the moon is marked with great symmetrical rings of deposit, umbrella shapes, drawn by material thrown up and falling evenly back. The lava reaches temperatures around 1,600 Kelvin. That is hotter than anything erupting anywhere on Earth today, and closer to the kind of eruption our own planet produced in its distant past, when the interior still held more of its original heat. Lava lakes hundreds of kilometers across sit on the surface and resurface episodically, brightening over the course of months and then fading again. The colors, the yellows and whites, the oranges, the reds, the black patches, come from sulfur and sulfur dioxide in their various forms and states. It is not a decorative fact. It is an inventory of a world venting its own interior continuously and painting itself with the result. The shape of Io's volcanoes is worth noting, because it is not the shape most people picture. There are very few cones. The dominant feature is the patera, a broad, flat-floored depression with steep walls, something like a caldera, formed where the roof over a magma chamber has collapsed rather than where material has piled up around a vent. Io has hundreds of them, some more than 100 kilometers across, and many are dark because their floors are covered in cooling lava rather than sulfur frost. There are mountains too, and they are not volcanic at all, which is one of the more unexpected things about the moon. Some of them rise more than 10 kilometers above the surrounding plains, higher than anything on Earth measured from its base. They appear to be blocks of crust thrust upward under compression. If a world buries its own surface at a centimetre a year, then every part of that crust is being pushed steadily downward and inward, and somewhere that material has to go. It goes up, in slabs, tilted and fractured, standing over the sulfur plains like broken paving. Io has an atmosphere, and it is one of the strangest arrangements anywhere. It is mostly sulfur dioxide, at roughly a billionth of Earth's pressure, sustained partly by direct volcanic venting and partly by frost on the ground sublimating in sunlight. On the night side, and during the roughly 2 hours of each orbit that Io spends inside Jupiter's shadow, the temperature falls far enough that the atmosphere condenses out onto the surface and effectively collapses. When the light returns, it lifts again. Io's atmosphere freezes and thaws twice in every 42 hours, and has done so continuously for as long as the moon has been where it is. There is also an electrical connection, and it is the detail that makes Io feel less like a satellite and more like a component. Io moves through Jupiter's magnetic field at high speed, and a conductor moving through a magnetic field generates a voltage across itself. The potential difference across Io is on the order of 400,000 volts. Current flows along the magnetic field lines connecting the Moon to Jupiter's polar regions, and that current is measured in millions of amperes, carrying something like a terawatt of power. The visible consequence is a bright spot in Jupiter's aurora, Io's own footprint, glowing in the planet's polar light, moving as Io moves, with a luminous tail trailing behind it. Io is not merely orbiting Jupiter, it is wired into it. And Io is leaking. Roughly a ton of material escapes the Moon every second, ionized and swept up by the magnetic field, and it forms a torus of plasma encircling Jupiter along Io's orbital path. That torus is what inflates the entire Jovian magnetosphere from the inside, a structure unlike Earth's, which is shaped almost entirely by the solar wind pressing in from outside. Jupiter's is shaped substantially by one small moon breathing sulfur into it. Long before any spacecraft arrived, astronomers on Earth detected a cloud of neutral sodium around Io through telescopes, without at first knowing where it came from. Which brings us to the number that closes the case on Io as a destination. If Europa's 5.5 sieverts per day is severe, Io's is worse by something like a factor of 6 or 7, around 36 sieverts per day. That is a certainly fatal dose in a couple of hours, delivered to a surface that is also being repaved beneath your feet, in an atmosphere that condenses onto the ground every night, on a world that flexes 100 meters twice a day. There is a quiet symmetry in that arrangement which is easy to miss. Io is the source of the radiation environment, and one of its principal victims at the same time. The sulfur it vents becomes the plasma that fills the magnetosphere. The plasma is accelerated by Jupiter's spin, and the accelerated particles come back down onto Io's own surface, harder than they fall anywhere else. The Moon is being punished with material it supplied. Nothing about it is separable from anything else about it. No spacecraft has ever landed on Io. None is seriously proposed. It is, without much competition, the most hostile solid surface in the solar system, and the reason it is worth spending this long on it is that its violence and Europa's ocean are the same phenomenon. The resonance that keeps Io molten is the resonance that keeps Europa's water liquid. Remove one and you remove the other. There is no version of this system in which the ocean exists and the neighborhood is calm. Io also has the most extraordinary view in the solar system, which almost nobody mentions. From its surface, Jupiter spans about 19 degrees, nearly 40 times the width of the full Moon from Earth. It is the largest any planet appears from any solid ground anywhere in the solar system, and because Io is tidally locked, it never shifts by a degree. It hangs there, motionless, filling a great arc of the sky, banded and turning, over a landscape of sulfur and slow fire, and plumes rising silently into vacuum. It has hung there for billions of years, and it will hang there for billions more, and it is entirely possible that no eye will ever see it. Part 7. Ganymede, the one that almost works. Before we go outward again, it is worth gathering up what we have so far, gently, in the way you might lay out a few objects on a table before deciding what to do with them. There is a planet with a magnetic field larger than anything else in the solar system, turning once every 10 hours and dragging that field around with it. There are trapped particles inside that field, accelerated to enormous energies, sweeping past every moon in the system. There is a gravitational resonance among the 3 inner moons that keeps their orbits stretched and their interiors warm. And there are the 2 consequences of that arrangement, sitting side by side: Io, molten and paved and unreachable, and Europa, smooth and cracked and hiding twice Earth's water beneath a shell of ice that would take a lifetime to drill through, under a sky delivering 5.5 sieverts a day to anything standing on it. Now we move outward, and the picture changes character. The next moon out is larger than the two we have seen, farther from the planet, and it is the first one where the answer to the question of habitability is not simply no. Ganymede is the largest moon in the solar system, about 5,270 kilometers across. That makes it larger than the planet Mercury and about 3/4 the diameter of Mars. If it happened to orbit the Sun instead of Jupiter, nobody would hesitate to call it a planet. It circles Jupiter at roughly 1 million kilometers in a little over 7 days, tidally locked like its neighbors, with a surface gravity a shade above Europa's, still about 1/7 of Earth's. Its surface is divided between two kinds of ground, and the division is visible from a great distance. About 1/3 of it is dark terrain, ancient, heavily cratered, dating back close to the formation of the system. The rest is lighter grooved terrain, younger, cut into long parallel ridges and troughs that run for hundreds of kilometers in sets, like the marks of an enormous comb. Those grooves are extensional. The crust was pulled apart, not pushed together, which implies that at some point in its history, Ganymede expanded. That is what happens when water inside a body freezes and takes up more room than it did as liquid. The dark terrain is dark for a straightforward reason. Over billions of years, the ice in it has slowly sublimated away into space, leaving behind a residue of dust and rocky material that never left. The same process darkens the outermost moon, and we will see it there in a more advanced state. But the thing that sets Ganymede apart from every other moon in the solar system is not visible at all. Ganymede generates its own magnetic field. It is the only moon known to do so, the product of a dynamo operating in a liquid iron core, the same basic machinery that gives Earth its field. And because Ganymede sits inside Jupiter's much larger field, the result is something that exists nowhere else we know of, a magnetosphere nested inside another magnetosphere, with a boundary between them and its own set of poles and field lines and auroral zones. The practical effect is partial protection. Charged particles arriving from Jupiter's belts are deflected around Ganymede's equatorial regions and funneled instead toward its magnetic poles. The polar caps take the bombardment, the low latitudes are shielded. You can see the difference from orbit. The poles are visibly brighter than the rest of the moon, their surfaces altered by particles landing on them, so that Ganymede wears two bright caps that are nothing to do with cold and everything to do with magnetism. The dose in the shielded equatorial band is around 8 rem per day, roughly 0.08 sieverts. That is about 70 times lower than Europa's figure, and the difference is not a difference of degree. It is the difference between a place that kills a person in a day and a place that kills them over months. It is still, to be clear, something like 1,000 times Earth's natural background, and far beyond any occupational limit anyone would sign off on. But it moves the problem from the category of impossible into the category of expensive, and that shift is the whole reason Ganymede is worth discussing at all. Ganymede also has an ocean, and the evidence for it is once again indirect and once again convincing. The moon's aurorae, visible in ultraviolet light, ringing the magnetic poles, rock back and forth as Jupiter's tilted field sweeps past. They should rock a good deal more than they do. Something inside the moon is generating an opposing field that damps the motion, and the only plausible candidate is a layer of salty, electrically conducting water. And then comes the disappointment, which is a disappointment of size. Ganymede is much bigger than Europa, and size changes what happens to water inside a body. Under sufficient pressure, water freezes again, not because it becomes colder, but because it is squeezed. There are high-pressure forms of ice that remain solid at temperatures well above the ordinary freezing point, and in a body Ganymede's size, the water layer is deep enough to reach those pressures at its base. The likely structure is layered. An outer crust of ordinary ice, perhaps 150 kilometers thick. Beneath that, liquid water. Beneath the water, a layer of dense, high-pressure ice, and possibly further alternating layers below that, an arrangement sometimes described, not unfairly, as a sandwich. And underneath all of it, the rocky mantle. That geometry is the problem. If a layer of solid ice sits between the ocean and the rock, then the ocean never touches mineral surfaces. There are no hydrothermal vents. There is no serpentinization releasing hydrogen, no dissolution of minerals supplying nutrients, no chemical gradient anywhere for anything to live on. Ganymede holds considerably more water than Europa. Its ocean may be several times the volume, and it may be the less promising of the two, precisely because it holds so much. The water is sealed away from everything that could make it interesting. Ganymede is also fully differentiated, which for an icy body is unusual and tells you something about its past. Its interior has separated cleanly into an iron core, a rock mantle, and an outer envelope of ice and water, and that separation only happens if a body is warm enough, for long enough, for dense material to sink through it. Ganymede was once considerably hotter than it is now, and its layered interior is the record of that. It has since cooled, but the core remains liquid enough to keep the dynamo turning, which is why the field is still there. Above the surface there is the faintest trace of an atmosphere, produced the same way Europa's is, radiation breaking water molecules in the ice and releasing oxygen, with the hydrogen escaping first. Traces of ozone have been found in the ice as well, formed by the same bombardment. And in the sky above all of it, Jupiter spans about 7.5 degrees, some 15 times the width of the full moon from Earth. Still an enormous presence, still permanently fixed in one place, but no longer filling the view the way it does from the moons further in. As a place for people, though, Ganymede is the reasonable compromise, and it is the only one of the 4 inner worlds where the compromise is even available. The equatorial band is survivable with real but achievable shielding. The surface is ancient and stable, rather than being repaved. The moon is large enough to offer genuine resources, water ice in enormous quantity, rock mixed through the crust, and the gravity to hold on to whatever is brought there. And it is the only body in the system besides Earth's own planet that comes with a magnetic field of its own. The costs remain. A 7-day orbit means long cycles of light and shadow, and a long eclipse within each one. The dose is high enough that surface work would be rationed by accumulated hours, rather than by daylight or by supplies. And Ganymede is still close enough in that a disturbance in Jupiter's magnetosphere raises the dose sharply, without warning, with nothing to be done about it except to already be underground. A large spacecraft is on its way there now, intended to enter orbit around Ganymede and stay. If it succeeds, it will be the first time anything of ours has orbited a moon other than our own, a small first, and a quiet one, and the beginning of a much longer look at the largest moon there is. Part 8. Callisto, the only ground a person could stand on. The outermost of Jupiter's 4 great moons is Callisto, and it is the one nobody talks about. It orbits at roughly 1.9 million kilometers from the planet, nearly twice as far out as Ganymede and more than 4 times as far as Europa, taking about 16.75 days to go round. It is almost exactly the size of Mercury, though far less massive, and its surface gravity is about 1/8 of Earth's. The single most important fact about Callisto is a negative one. It is not part of the resonance. The gravitational conversation that keeps Io molten and Europa's ocean liquid does not include it. Its orbit was never forced elliptical, it was never repeatedly squeezed, and so it was never heated. Almost everything else about the moon follows from that absence. Callisto's surface is the oldest in the solar system, and it is saturated with craters. That word has a precise technical meaning. The surface has accumulated impacts for so long that every new crater now destroys an existing one, and the total number has stopped rising. There is nowhere on Callisto that has not been struck. It is, by a comfortable margin, the most heavily cratered object we know of anywhere. Its dominant feature is an enormous multi-ring impact structure, a bright central patch surrounded by concentric rings that spread outward across nearly 4,000 kilometers of the Moon's face. It formed when a large body struck ground that was cold but not entirely rigid, so the surface rippled outward like water disturbed by a stone and then froze in place with the ripples still in it. From a distance, the whole hemisphere reads as a target, or as a set of rings drawn around a bright center by something very patient. The ground itself is dark for an icy body. It reflects only about a fifth of the light that falls on it, against Europa's 2/3. The reason is time. Over 4 billion years, the exposed ice has slowly sublimated away, molecule by molecule, into space, and what it has left behind is a lag deposit of dark dust and rocky material that could not evaporate. Bright ice still shows at crater walls and along fresh scarps, where more recent disturbance has cut through the dark layer and exposed what lies beneath. So Callisto reads as dark ground with white highlights, like an old road surface after rain. There is a subtlety in those craters worth pausing on. On a rocky world, a crater rim keeps its shape more or less indefinitely. The material is strong enough to hold the form it was given. Ice is not. Over hundreds of millions of years, ice relaxes under its own weight, even at 130 Kelvin, flowing so slowly that the motion could never be watched, and crater rims sag and soften and settle back toward the level. Callisto's craters are noticeably more degraded than equivalent features on rocky bodies of the same age, and none of that softening required an impact, or an eruption, or heat. It required only time, and Callisto has had more of that than anywhere. In places, the erosion has produced something stranger. Where sublimation has stripped ice away from around more resistant material, it has left behind isolated knobs and spires standing a few hundred meters above the surrounding plain, the last remnants of ground that has otherwise evaporated out from under them. They are not mountains. They are what is left when everything around a thing quietly disappears. There is even the barest trace of an atmosphere, a tenuous exosphere of carbon dioxide with a component of molecular oxygen, continuously leaking from the surface and continuously being lost, replenished just fast enough to still be there. And here is why Callisto matters, and why the whole shape of this episode turns around at this point. Callisto orbits outside the most intense part of Jupiter's radiation belts. The dose at its surface is of order 0.01 rem per day, roughly a 10,000th of Ganymedes, and something like a millionth of Europa's. Put differently, a person could stand unshielded on Callisto's surface for an entire year and accumulate a dose comparable to a few years of ordinary background radiation on Earth. Callisto is the only solid surface in the entire Jovian system that a human being could stand on, without the standing itself being what kills them. That fact has not gone unnoticed. When mission architects have looked seriously at crude exploration of the outer solar system, Callisto is the destination that comes back. It is the place to build the base, refuel the vehicle, store the supplies, and, critically, to operate machinery at the inner moons from a distance. A person on Callisto could drive a rover on Europa with a signal delay of a few seconds. A person on Earth would wait more than an hour for each exchange. That single difference is the strongest argument anyone has ever made for putting people in the Jovian system at all. Not to walk on the interesting moon, but to be close enough to properly operate something that does. There is a second advantage that follows from the same geometry. Because Callisto lies outside the harshest belts, a spacecraft can approach it, enter orbit around it, and leave again without accumulating the kind of dose that shortens a vehicle's life at the inner moons. Everything about operating there is easier. The electronics survive, the solar-facing surfaces last, the instruments keep their calibration. The moon that is safest for a person is also the safest for the machine that carried them, and that is not a coincidence. It is the same number, applied twice. Callisto's interior reflects its history of never having been warmed. It is only partially differentiated, its rock and ice never fully separated into distinct layers, and the interior grades gradually from rock-rich at the center to ice-rich at the outside, without the sharp boundaries that Ganymede has. It is, in a sense, a body that was assembled and then simply left as it was. There is nonetheless magnetic evidence for an ocean, probably 100 kilometers or more down, salty and cold, and almost certainly separated from the rock beneath it by the same high-pressure ice that isolates Ganymedes. It is the least promising of the system's 3 hidden seas, and the deepest buried, and the least likely ever to be reached. So Callisto is safe. But the safety is the safety of exile, and it is worth being clear about what has been traded for it. There is no tidal heating, which means no internal energy source, no volcanism, no warm layer anywhere near the surface, and nothing at all driving chemistry. The ground is a dusty residue over ancient ice at around 130 Kelvin, and it has been geologically motionless for longer than complex life has existed on Earth. There is no tectonic activity of any kind. Nothing on Callisto has moved by itself, apart from things falling onto it, since before the sun had finished settling into its present brightness. Sunlight there is the same 4% of Earth's, so power is nuclear power, with all that implies about depending on hardware that cannot be replaced locally. The orbit takes nearly 17 days, which means roughly 8 consecutive days of darkness for any surface operation. Communication with Earth runs to more than half an hour each way, and there is no rescue. There has never been a place people have lived on Earth. No polar station, no submarine, no expedition. That was more than a few weeks from help. Callisto is years from it. The sky there is quieter too, and the quietness is the last measure of how far out it sits. Jupiter from Callisto spans about 4 degrees. That is still 8 times the width of the full moon from Earth, and it is still fixed in one place forever, and it is still an extraordinary thing to have overhead. But it no longer fills the view. It no longer dominates. From Io, Jupiter is a wall. From Europa, it is a presence you could not look away from. From Callisto, it is a large, calm, banded circle in a dark sky, with 3 bright points of light moving slowly in front of it and behind it, and a very small sun somewhere off to one side. That is the balcony of the Jovian system. Far enough out to be survivable, far enough out that almost nothing happens, and near enough to watch everything that does. It is not the destination anyone imagines when they imagine going to Jupiter. It has no ocean worth reaching, no volcanoes, no magnetic field, and nothing to discover that a single good orbiter could not establish in a year. What it has is ground you could walk on, and in this system that turns out to be the rarest thing there is. Part 9, the other 90, and the rings they make. The 4 great moons hold essentially all of the mass in Jupiter's satellite system. Everything else that orbits the planet, and there are more than 90 confirmed objects, with the number still rising as survey telescopes improve, amounts together to a rounding error. But those small bodies are not incidental, and 2 of them are the reason Jupiter has rings at all. Inside Io's orbit, there are 4 small moons, and they live in a region that no larger body could survive. The 2 innermost are irregular lumps a few tens of kilometers across, orbiting closer to Jupiter than anything else we know of, and they orbit faster than Jupiter turns. That is an unstable arrangement. When a satellite circles a planet more quickly than the planet rotates, the tidal interaction between them removes orbital energy rather than adding it, and the satellite slowly descends. Both of these moons are spiraling inward. The timescale is far longer than human history, and far shorter than the age of the solar system, and at the end of it, they will come apart and fall into the planet. The larger two of the inner moons are more substantial bodies. One of them measures roughly 250 kilometers along its longest axis and is shaped rather like a potato, and it is the reddest object in the solar system, redder than Mars, redder than anything. It is also less dense than water, which is a genuinely surprising measurement, because it means the moon cannot be a solid object. It has to be a loosely bound pile of rubble, with a great deal of empty space distributed through it, held together by little more than its own very weak gravity. And its color appears to be borrowed, sulfur from Io, ionized and carried outward and driven into its surface, the same contamination that stains Europa's trailing side. That a rubble pile survives at all so close to Jupiter is itself worth noticing. There is a distance from any large body inside, which tidal forces exceed the self-gravity holding a loosely bound object together, and anything that strays inside it is pulled apart. These inner moons sit close to that boundary. They are not comfortable there. They are small enough, and just far enough out, and just strong enough internally to persist, and the persistence is provisional rather than permanent. The whole inner region has the character of a place that is still being cleared. Anything large that formed there is gone. What remains are a handful of small survivors, moving very fast, in a region flooded with radiation, close enough to the planet that Jupiter fills nearly half the sky as a curved luminous wall with no visible edges to it. These small moons are the source of the rings. Micrometeorites strike them continuously, as they strike everything without an atmosphere, and each impact throws up a small quantity of dust. On a large moon, that dust would fall back. On bodies this small, with gravity this weak, much of it simply leaves, and once it has left, it is in orbit around Jupiter. That escaping dust is Jupiter's ring system. The rings are nothing like Saturn's. They are not ice, they are not bright, and they were not detected from Earth at all. They were found when a spacecraft that had already passed the planet turned and looked back at it with the sun behind, and saw them in forward scattered light, which is the only geometry in which such fine dark dust becomes visible. There is a flat main ring, an inner halo that puffs upward out of the ring plane, and two exceptionally faint outer sheets called the gossamer rings. The structure is legible if you know what to look for. Each gossamer ring has an outer edge that corresponds exactly to the orbit of one of the small inner moons, because that is where the dust comes from, and it does not travel outward past its source. And the halo ring is thick rather than flat, because the dust grains in it carry electric charge, and Jupiter's magnetic field lifts charged particles out of the plane they started in. The rings are not simply debris. They are a magnetic system with debris in it. They are also temporary in a way Saturn's rings are not. Ring particles that fine have lifetimes of perhaps thousands of years before they spiral in or are swept away, which means the entire structure must be continuously resupplied by fresh impacts on the small moons, or it would already have vanished. What we see is not an ancient feature. It is a steady state, maintained. Beyond Callisto, the character of the system changes again and becomes something closer to a swarm. At distances of 10 to 30 million kilometers from Jupiter, 5 to 15 times farther out than Callisto, there are dozens of small irregular moons. Most are only a few kilometers across. Their orbits are tilted, elongated, and in many cases retrograde. They travel backwards around Jupiter, against the direction of the planet's rotation and against the direction everything else in the system moves. That retrograde motion is the clue to what they are. Nothing forms in retrograde orbit around a planet. Material condensing out of a disk around a young world all moves the same way, because the disk did. Anything going the other way must have arrived from outside and been captured. Asteroids and comet nuclei that passed too close, lost enough energy to some interaction, and never left. Most of them were found recently, and most of them were found by accident. The swarm is faint, a body 4 kilometers across, painted in the dark material typical of the outer solar system, at 20 million kilometers from a planet that is itself 500 million kilometers away, reflects an almost negligible quantity of light. Every improvement in the sensitivity of survey telescopes turns up more of them, and the count has climbed steadily as a result. It is very likely that the true number is considerably larger than the confirmed one, and that most of Jupiter's moons have not been seen yet. They cluster into families. There is a prograde group orbiting at around 11.5 million kilometers, and several retrograde groups considerably farther out. Within each family, the members share orbital characteristics closely enough that they cannot be independent captures. They are fragments. A single body was captured, and then at some point it was struck and shattered, and its pieces have continued along nearly the same path ever since, gradually spreading out along it. Their orbital periods run from around 6 months at the inner edge of the swarm to nearly 3 years at the outer. Some of the outermost are only marginally bound at all. At those distances, the Sun's pull competes seriously with Jupiter's, and a body there is held loosely enough that a modest disturbance could take it away entirely. From out among them, Jupiter is no longer a wall or a presence. It is a bright disk a fraction of a degree across, recognizably a planet with a visible shape, with 4 bright points of light attending it, and nothing more. The great magnetic field that governs everything closer in does not reach that far, and the swarm sits in ordinary sunlight and ordinary quiet. They are, in every practical sense, useless. Too small to hold anything down. Too dark and too numerous to have been properly catalogued. Too far out to serve as a staging point for anything. But they are worth a moment because of what they are. Several dozen pieces of the early solar system, gathered up by accident and kept, orbiting slowly in the outer reaches of a system that has never done anything with them at all. They were formed somewhere else, out of material that never became part of Jupiter or of any of its great moons, and then they wandered close and were caught, and they have been going round ever since without ever being warmed, or resurfaced, or struck by anything larger than themselves. Whatever they were made of at the beginning, they still are. In a system defined everywhere else by violence and heat and continuous alteration, the outermost objects are the only ones that have been left entirely alone. Part 10. The Crossing, and what it costs to stay. Everything we have discussed so far assumes arrival, and arrival is the part that is quietly hardest. Jupiter sits at about 5 times Earth's distance from the Sun. A minimum energy transfer, the cheapest possible path, an ellipse touching Earth's orbit at one end and Jupiter's at the other, takes a little under 3 years and arrives traveling much too fast to stop. Real missions do something more patient. They loop back through the inner solar system first, taking gravitational assistance from Venus and from Earth, gaining speed a little at a time without spending fuel for it, and arrive 6 or more years after leaving. Launch opportunities recur roughly every 13 months when Earth and Jupiter are correctly arranged, and missing one means waiting for the next. But the journey out is not the expensive part. The expensive part is stopping. The energy needed to leave Earth's vicinity for Jupiter is, remarkably, not much greater than the energy needed to reach low orbit around Earth in the first place. Getting off the ground is the difficulty. Once you are up, the solar system is comparatively open. What costs is arriving somewhere and remaining there. To be captured into orbit around Jupiter rather than flying past it, a spacecraft has to shed a great deal of velocity, and the most efficient place to do that is deep in the planet's gravity well, close in, which is precisely where the radiation belts are worst. Every mission to Jupiter has had to trade propellant against dose on the way in, and the trade has no good answer. Slow down further out, and you spend more fuel. Slow down closer in, and you spend more of the spacecraft. There is a concept for avoiding the trade entirely, called aerocapture, dipping into Jupiter's upper atmosphere on arrival and using drag to shed the excess speed, then climbing back out into a captured orbit. It requires no propellant at all. It also requires flying a vehicle through the outer atmosphere of the largest planet in the solar system at tens of kilometers per second, with heating and structural loads beyond anything ever attempted, and a corridor a few kilometers wide that must be hit after a 6-year crossing. It has never been done anywhere, by anyone, at any planet. For a crewed vehicle, the arithmetic turns on itself in a way that is worth following slowly, because it explains why the problem is harder than it first appears. The crew must be shielded for the entire crossing against cosmic rays and against whatever the sun does in the 6 years they are exposed to it. They must be shielded far more heavily for the arrival, when the ship comes in close to shed speed. And they must be shielded permanently once they are there. Shielding is mass. Mass requires propellant to move. Propellant is itself mass, which requires propellant of its own to move, and so the requirement compounds against itself at every stage. This is why the Jovian system is not simply far away in the sense of being a long way to point a rocket. It is far away in the sense that every additional kilogram of safety multiplies through the entire vehicle. There is one welcome exception, and it applies once you have arrived. All 4 of these moons have low escape velocities, 2 kilometers per second at Europa, not much more at the others, against Earth's 11. Moving between them, once you are already inside the system and traveling with it, is comparatively cheap. A modest vehicle could lift from Callisto, cross to Ganymede, descend, and lift again, on quantities of propellant that would not get a similar vehicle off the ground at home. The expensive parts of a Jupiter mission are the beginning and the end. The middle of it, the part that involves actually visiting 4 worlds, is the easy part. Once there, the second constraint arrives, and it is not physical but conversational. A signal takes between 33 and 53 minutes to travel one way between Earth and Jupiter, depending on where the 2 planets are in their orbits. A question and its answer are separated by more than an hour, at the very best. There is no real-time control of anything. There is no supervision, no consultation, no calling home for a decision, and no possibility of anyone on Earth intervening in a situation that is developing on any human timescale. A crew at Jupiter is autonomous whether or not it wishes to be, and whether or not it is ready to be. That single fact is the strongest argument that exists for putting people in the Jovian system at all, and it points directly at Callisto. A person standing on Callisto could operate a machine on Europa's ice with a delay of a few seconds, near enough to real time to drive, to react, to correct a mistake before it becomes an accident. The same machine operated from Earth would wait more than an hour for every instruction and every acknowledgement, which means it can only ever execute plans, never respond. The difference between those 2 situations is the difference between exploring a place and merely visiting it very slowly. Then there is power, and the arithmetic there is simple and severe. Sunlight at Jupiter is about 4% of what falls on Earth. Solar arrays sized for Earth conditions would need roughly 27 times the area to deliver the same output, and they would have to survive a radiation environment that degrades semiconductors continuously. Missions have flown large solar arrays that far out, and they work, and they are enormous, and they supply a few hundred watts where an equivalent array at Earth would supply many kilowatts. For a spacecraft, that is workable. For a settlement, it is not. Radioisotope sources, the small nuclear batteries that have powered every long-duration mission to the outer system, supply a few hundred watts each and decline by a few % every year as their fuel decays. That is enough to run instruments and a transmitter for decades. It is nowhere near enough to run a habitat, life support, heating, lighting, and the machinery to melt and process ice. So a settlement in the Jovian system runs on fission, which means its continued existence depends indefinitely on hardware that cannot be manufactured locally for a very long time, and that must be brought across 5 astronomical units, and that must then be maintained by whoever is there with whatever they happen to bring. Against all of that, there is one genuine abundance, and it is the reason the system remains attractive despite everything else. Water. 3 of the 4 great moons are made substantially of it, and much of it is simply lying on the surface as ice, requiring no drilling at all to reach. Only the deep ocean is deep. Water is drinking supply. Split it, and it is breathable oxygen and hydrogen for propellant. Stack it around a habitat, and it is radiation shielding, and better shielding than lead, for the reasons we saw earlier. It is the one resource that solves 4 problems at once, and the Jovian system holds more of it in accessible form than anywhere else beyond Earth. What the system does not offer conveniently is everything else. Metals and rock are what a settlement needs to grow rather than merely persist, and they are awkwardly placed. Europa's rock lies 100 kilometers beneath an ocean that lies 20 kilometers beneath ice. Ganymede and Callisto have rocky material mixed through their crusts, but mixed rather than concentrated, which means processing enormous volumes of ice to extract modest quantities of anything. Io has metal in abundance, and no water at all, and cannot be visited. There is one further resource sometimes mentioned, and it belongs in a different category of distance altogether. Jupiter's atmosphere contains helium-3, an isotope that would be a nearly ideal fusion fuel if we had reactors that could use it, and it contains a great deal of it. Proposals exist for scooping it out with vehicles that dive into the upper atmosphere and climb back out. Whether that is ever worth taking seriously depends on solving fusion first, and on being willing to fly repeatedly into the atmosphere of a planet with that gravity and that radiation environment. It sits far beyond everything else discussed tonight, in the part of the future that is genuinely speculative rather than merely difficult. None of the resource distribution is arranged for anyone's convenience. That is not a complaint about the system. It is simply what it is. The Jovian moons were assembled by physics that had no interest in whether the useful things ended up near one another, and 4.5 billion years later, they still do not. And the round trip, with any reasonable stay, comes to something like a decade. Nobody has ever been away from the surface of Earth for more than about 14 months. To go to Jupiter and come back is to be gone for roughly 10 times longer than anyone in history has managed, in a place with no rescue, no resupply that was not planned years in advance, and no conversation that does not have an hour's silence in the middle of it. Part 11. The slow accounting. There is a difference between what a place does to a person in an hour and what it does to them over years, and in the Jovian system, the second question is the harder one. Take the best case available. Callisto, or the shielded equatorial band of Ganymede, or a shelter buried 10 meters deep in Europa's ice. In every one of those places, the acute problem has been solved. Nobody is dying of an afternoon outdoors. What remains is an accounting problem, and the account never closes. Radiation exposure accumulates. It does not heal, it is not repaired, and there is no threshold below which the risk becomes zero. Chronic exposure at levels far below anything acutely dangerous still raises the lifetime probability of cancer, accelerates the formation of cataracts in the lens of the eye, contributes to damage in the blood vessels and the heart, and, in animal studies at doses relevant to deep space missions, appears to affect the central nervous system in ways that show up as changes in learning and behavior. That last effect is the least understood and the most concerning, because it touches the one system that cannot be shielded by being replaced. What that means practically is that everyone who went would be spending a fixed budget of health, drawn down steadily, whether or not anything was accomplished on any particular day. Time spent on the surface would be rationed by accumulated dose rather than by daylight or by supplies. Careers would be measured in sieverts rather than in years. And the budget would keep being spent through every hour of sleep, every meal, every quiet afternoon indoors, because the thing spending it does not pause. Then there is the gravity, and the size of what we do not know about it. All 4 of these moons sit between about 1/8 and 1/5 of Earth's gravity. Every long-duration dataset in human physiology comes from either 1 gravity or approximately 0. Between those 2 points there is nothing, not a partial answer, not a small study, nothing. It is possible that a modest fraction of Earth's pull is sufficient to keep bone and muscle and the cardiovascular system in reasonable order, and that a 1/7 would do. It is equally possible that the response is closer to a switch than a slope, and that a 1/7 is functionally the same as none. What we do know about the zero-gravity end of the range is not encouraging, and it is worth setting out plainly. Bone loss does not happen evenly across the skeleton. It concentrates in exactly the places that carry weight: the hips, the lower spine, the legs, because those are the structures the body maintains only in response to being loaded. Remove the load and the maintenance stops. The loss runs at something like 1 to 2% of mineral density per month, and it continues for as long as the condition does. On return to Earth, it recovers only partially, and in some cases the recovery is still incomplete years later. Exercise slows it considerably but has never been shown to stop it. Fluid behaves differently too. On Earth, gravity holds a great deal of the body's fluid in the lower half of it. Remove that, and the fluid redistributes upward, toward the chest and the head, and stays there. Faces become fuller. Sinuses stay congested. And the pressure behind the eye changes enough that in a substantial fraction of long-duration crew members, the back of the eyeball flattens slightly and vision shifts, sometimes permanently. It is one of the more instructive findings of the last 2 decades of spaceflight medicine, precisely because nobody predicted it. The immune system also drifts. Measurements consistently show dysregulation in long-duration crews, some responses blunted, others heightened, and dormant viruses that a healthy body would keep quiet reactivate more readily. In a sealed habitat, years from any pharmacy that was not packed in advance, that is not a minor observation. The uncertainty compounds for anyone who might be born there. Human development has never been observed under reduced gravity at any stage. Not gestation, not infancy, not the long business of a skeleton assembling itself over 18 years. A body that grew at 1/7 of Earth's gravity would be a body built for a world that only exists in one place, and whether such a person could ever safely visit the planet their ancestors came from is not a question anyone can currently answer. It is not a small question. It is the difference between an outpost and a place people live. And then there is the environment itself, which is unlike anything human beings have ever adapted to. There is no weather. Not bad weather, none. Nothing moves in the air outside because there is no air. No wind ever rises, no cloud ever crosses, no temperature ever changes for any reason other than the position of a very small sun. There is no sound outside the habitat, and no smell, and the light is permanently dim and permanently the same. There is no season, because these moons stand nearly upright on their axes, and their year is Jupiter's year, nearly 12 of ours, and even then it changes nothing, because the sunlight is too faint for the small variation to register. And there is no day. The rhythms on offer are a 3.5-day orbit at Europa, 7 at Ganymede, nearly 17 at Callisto, and none of them is anywhere near the roughly 24 hours that human biology insists on. Left without correction, the body's internal clock drifts, and it drifts consistently in the same direction, and the drift compounds. Every long-duration habitat design treats artificial lighting not as a comfort but as life support equipment, tuned to a 24-hour cycle, brighter and bluer in the morning, warmer and dimmer at night. Because without that manufactured day, the schedule comes apart within weeks. Above all of it, Jupiter does not move. On the near hemisphere, it hangs in exactly the same place it has occupied for billions of years, cycling through its phases, never rising and never setting. On the far hemisphere, it is not there at all. The ordinary background sense that time is passing, light shifting across a room, air moving, the year turning over, is simply absent, and everything that replaces it has to be built deliberately and maintained deliberately for as long as anyone is there. The psychological research that exists on long isolation, gathered in polar stations and submarines and long-duration crews, is consistent about one thing: the difficult period is not the beginning and not the end. It is the third quarter. Long after novelty has worn away, and well before return feels close enough to count down to. In a mission measured in years, that stretch would itself be measured in years. There is one more feature of the situation that has no precedent anywhere in human experience, and it is not the distance. It is the absence of any option to leave early. Every remote place people have ever worked on Earth, the deep polar stations, the submarines on long patrol, the high mountain expeditions, is at worst a few weeks from help, and everyone in those places knows it. The knowledge itself does work. It is the flaw under the situation. In the Jovian system, there is no flaw. There is no evacuation, no early return, no aircraft that could be sent, and no configuration of the planets that shortens the journey below years. Whatever happens has to be handled by the people who are already there, with what they already have, and that is a qualitatively different thing from remoteness. It is a different relationship with the idea of help. And Earth would be a point of light. From Jupiter, our planet is a faint star sitting very close to the sun in the sky, hard to separate from the glare and easy to lose. It is an hour away by any message and years away by any vehicle. Everyone who has ever left Earth so far has been able to look back and see it as a world, a blue disk, or at the very least a bright and obviously particular object. From the Jovian moons, it would not look like a place. It would look like a star that happened to be in the wrong part of the sky, and it would take a moment's searching to find. Part 12. What we are actually doing out there. So we arrive, at the end of a long evening, at 3 things that are worth carrying away, and none of them is that the moons of Jupiter are impossible. The first is that our instinct about which of them is the destination turns out to be exactly backwards. Europa is the one everybody names. It is the one with the ocean, the one that appears at the top of every list, the one that carries the possibility of life more plausibly than anywhere else within reach. And Europa's surface is the most lethal ground in the solar system. 5.5 sieverts a day, invisible, silent, arriving through the suit and through the skin, without a single sensation to announce it. Callisto is the one nobody names. It is old, dark, cratered, geologically dead, with an ocean too deep to reach and nothing at all happening on it. And Callisto is the only place in the entire Jovian system where a person could stand on the ground without the standing being what kills them. The moon we want is the one we cannot have, and the moon we can have is the one nobody wants. That is not a tragedy. It is simply how the system is arranged, and it is arranged that way by a single number, distance from Jupiter. The second thing is larger, and it runs underneath everything we have looked at tonight. All of this hostility is the same phenomenon as all of this promise. They are not opposed. They are not even separate. The radiation that would kill anyone standing on Europa is what manufactures the oxidants in its ice, and those oxidants may be the very chemical energy that an ocean sealed under 20 kilometers of ice would need in order to hold anything alive. The tidal flexing that shakes the shell 30 meters every 3.5 days and cracks it and rearranges it into chaos is the same flexing that keeps the water beneath it from freezing solid. The resonance that has turned Io into 400 volcanoes and 100 trillion watts of escaping heat is the identical resonance that keeps Europa warm enough to have an ocean at all. Remove any one of those and you remove the rest. There is no arrangement of this system in which the ocean exists and the neighborhood is gentle. The danger and the water are not two facts. They are one fact seen from two directions. And the reason Europa is worth going to is precisely the reason we cannot stand on it. The third thing is about presence, and it is the quietest of the three. We are already there. We have been, more or less continuously, for decades, not with people, but with machines, and the machines were designed from the beginning to die of the place. A spacecraft built for Europa is built around a radiation budget the way an aircraft is built around a fuel budget. Every close pass spends a measured portion of the vehicle's remaining life, and the mission plan states in advance how many passes there will be, because after that, the electronics will no longer be reliable. The end is written into the beginning. Nobody pretends otherwise. And there is one more thing those missions do that is worth sitting with as the night settles. When a spacecraft in the Jovian system reaches the end of its working life, it is not simply switched off and left in orbit. It is steered deliberately into Jupiter and destroyed. The reason is not tidiness. The reason is that an uncontrolled spacecraft would eventually drift, and over long enough spans of time, it might drift into one of the moons, and it might be carrying something from Earth, a spore, a fragment of biological material, something that survived the vacuum and the cold and the radiation of the crossing. Nobody has ever found life on Europa. Nobody knows whether it is there. And rather than take the chance of arriving uninvited, we plan the deaths of our own machines to make sure it cannot happen. That is a remarkable thing for a species to do. We have never seen that ocean. We may never see it. It sits in absolute darkness, under 100 kilometers of water, under 20 kilometers of ice, on a moon we cannot land on, 5 astronomical units away, and we are already being careful with it, protecting something we have no evidence exists, from ourselves, at real cost, on the strength of a possibility alone. It is worth saying what a realistic first human presence would actually look like, because it is nothing like the picture the phrase "living on Jupiter's moons" brings to mind. There would be no city on Europa. There would be no domes on the ice, no windows looking up at a banded planet, no one walking out under that enormous fixed face to plant anything. There would be a buried structure on Callisto, in the safest place in the system, surrounded by processed ice for shielding, running on a reactor brought from Earth. And from inside it, people would spend their days operating machines a long way away, driving rovers across Europa's cracked plains with a few seconds of delay, lowering probes into boreholes, watching through cameras that will be destroyed by radiation within a year, and replacing them when they are. The people would almost never leave. The machines would go to the interesting places, and the machines would not come back, and that arrangement would not be a compromise or a failure. It would be the correct design, arrived at honestly, by working through exactly the numbers we have worked through tonight. So when we say that living on Jupiter's moons would be harder than anyone imagines, all of that is true. The dose figures are true. The ice as hard as granite is true. The 30-meter flex, the 17-day night, the hour of silence in every conversation, the decade away. All of it is true, and none of it is likely to change. But it is worth remembering what is on the other side of that ledger. Twice Earth's water, in the dark, kept liquid for 4.5 billion years by nothing but the pull of a planet overhead. A moon with its own magnetic field, larger than Mercury, wearing 2 bright polar caps that have nothing to do with cold. A world of 400 volcanoes wired to its planet by 3 million amperes of current. An ancient dark surface that has not moved since before anything on Earth had a spine. A ring system made of dust, knocked off 2 rubble piles and lifted out of its own plane by magnetism. And 90 small captured things in the outer dark, going quietly round, unheated and unaltered, exactly as they were on the day they arrived. Every one of those is real, and every one of them was unknown to anyone alive 2 lifetimes ago, and we found all of it by sending a handful of machines out into the dark and paying close attention to what came back. They will all keep doing it. The ocean will go on turning under the ice, whether anyone ever reaches it, whether anything lives in it, whether we ever find out. That is not a sad thought. There is something restful in a place that does not require us in order to continue. And so we leave them where they have always been, 4 great worlds and 90 small ones, turning in the light of a star too far away to warm them, held inside a magnetic field that has never once let go. Somewhere beneath Europa's ice, in water that has never seen the sun, the ocean goes on moving, whether or not anyone is ever there to find it. Let your breathing slow. Let the day settle behind you. Sleep well, and good night.